Yeah, the answer sheet, it's almost done. It's almost, I can post it up in terms of what I have at the moment, just so that you all can and then I'll update it. Okay, so I'll do that right now. Give me one sec. All right, so 2.2 part 3. Let's start from the beginning. 2.2 part 3. Wait, no, that's not the one. 2.2 part 3. This one here, right? Is that the one? In the pre?
Yes, Professor.
Yeah. So I'm not gonna do all of them. I'm just gonna do one of them, and then you see how to do the rest. Okay. Because all these problems in that little section there are pretty much the same styled uh, procedure. Hold on. Okay, so they didn't catch it. Hold on one second. Let me try this again. Okay, I forgot to do that. Okay. All right. So we have so Xavier, the answer sheet is under the same place where the answer sheet number 2 is. So it's exactly in the same folder. It's under content, review sheet, and answers, and then it's under the review sheet for exam number 2 folder, and it's right there. All right, so the idea behind this problem is the same for all parts of it, A, B, C, and D, right? The reason why I give you all of these is just for added repetition and practice. It's not that because you do this one and you do these, um, you know, just doing all of them gives you more of a repetition, and things start to ingrain a little bit more. So if you're able to do A, theoretically you can do all of them, but of course you always have to practice. So let's look at part A. The question is the V that they give us 2, 3, negative 7, 3, is this in the span of V1, V2, V3? Right? That's the question. Is it in the span? If so, then what is positive? Then what's true? If your vector is in the span of a set of in the span of a set of vectors, that means that this vector can be written as a linear combination of the rest of those vectors. So then the question becomes, can I write this as C1 V1 plus C2 V2 plus C3 V3? That's the question. So then let's rewrite this as 2, 3, negative 7, 3. And then this equals C1 V1 is 2, 1, 0, 3 plus C2 is 3, negative 1, 5, 2 plus C3 is negative 1, 0, 2, 1. And then this becomes a system of equations. I can create a system of equations, right? And I can create from right here. I don't even have to write the system of equations. I can just create the matrix equation. This becomes 2, 1, 0, 3, the first column. Second column, 3, negative 1, 5, 2. And then the last column, negative 1, 0, 2, 1. And then this is C1, C2, C3. And this equals 2, 3, negative 7, 3. So I'm trying to solve this equation. I'm trying to find out what are these entries here. So the best bet from here, right, is to create an augmented matrix. So it's 2, 1, 0, 3, 3, negative 1, 5, 2, and negative 1, 0, 2, 1. And you augment it with this column vector, 2, 3, negative 7, 3. And from here, what I'm going to do is I'm going to apply row reduce. I'm going to find a row reduced echelon form of this. That's the best bet because we have a overdetermined system, which means I have more equations, or in this case, rows, than I have columns. I have only 3 variables, but then I have 4 equations. What problem is this? Well, welcome, Leo. We are on problem, what is this? 2.2, number 3. So we're in spanning sets and we're doing number 3 and we're doing part A. So part A asks, is the vector V in the span of the 3 vectors that we have? If it is in the span, then I can write it as a linear combination of the rest. If I can't express it as a linear combination, then it's not in the span. And so how do we test that? How do we test that? Well, we can create a matrix equation. And we will write this matrix equation. I have this matrix of coefficients, coefficient matrix, multiplied by this column vector, which are the unknown scalars which I'm looking for if it exists. And this equals the vector that we originally start with, right? So from here, I would recommend using your calculator for this. So this would be an help from the calculator. If not, you could do it by hand with row reduce and row reduce it, but I wouldn't recommend given time constraint. So then I'm going to not do that. This is math 231. So I'm going to go to create a 4x4 matrix because I have 4 rows and 4 columns in this augmented matrix. So I got first row 2, 3, -1, 2, 1. Whoops. Should be 2, right? And then I got 1, -1, 0, 3. Then I have 0, 5, 2, -7. Oh, what? 0, 5, 2. I don't know why. 0, 3, 0, 5, 2, and then I got -7. -7. And then 3, 2, 1. 3, 2, 1. 2, 1, and then 3. Then from here, I use the one of the math functions with row reduced echelon form. And I stick that matrix into that function and I get this. So let's interpret what this is saying. This is 1, 0, 0, 2. This is 0, 1, 0, -1. This is 0, 0, 1, -1. And I get a row of zeros in the bottom. Oh, yeah. So Gershon, I just saw your question. You can't just do AX equals B and switch it to AX equals inverse of AB. And it's because it's hard, like he says, it's overdetermined. So remember, Gershon, that the inverse only can even be spoken of when we talk about square matrices. Our original matrix, coefficient matrix, is non-square. So whenever that's the case, I have to resort to the only procedure that works for any kind of matrix, which is performing Gauss-Jordan elimination to get the row reduced echelon form. That's why we go back to the basics, to the beginning. The whole inverse thing is kind of like a cheat code in a way, because when it does exist, then things become very nice, right? So this whole idea of invertibility is very nice if it exists, if it's applied. If it's not, then you have to resort to more elementary, rudimentary operations, such as Gauss-Jordan elimination, so that you get the row reduced echelon form. And in this case, I'm able to get that. But then what does this row reduced echelon form give me? Well, remember that this is the augmented column, and the other columns are representing the three variables. So if we read this first row off, we're really saying x1 is equal to 2. So essentially, we solve the system. X2 is equal to -1, and x3 is equal to -1. Or I should say, maybe I should be more consistent with the coefficients that we're using here. We're using C1, C2, and C3. These are my unknowns. And so I solve the system. What's the significance of solving the system? Well, I figured out a way to write my V vector as a linear combination of V1, V2, V3. So I can write V, I can literally write V as 2 times V1 plus, or in this case, minus V2 minus V3. So then the result or the conclusion is V is indeed in the span of V1, V2, and V3. So the question says, determine if the following vectors are in the span. Well, A is. It is. Yes. It is. Why is it? Well, I just showed why. I found the coefficients that are the scalars associated with the vectors V1, V2, V3 that can write V, kind of express V as a linear combination of V1, V2, V3. And I just did that right here. Does that make sense? So V is a linear combination of V1, V2, V3. I'm not going to continue. Sorry, the series popped up. I'm not going to continue with the rest of these because the process now will become repetitive. It's the same idea. I'm going to write the same thing. I'm just going to replace V every single time. So all of these guys here, I'm just going to replace this vector with each one of these and do the same thing. This is going to be different. All of these things here are always going to be the same. It's going to be the coefficient matrix with this. Yeah, for span, that's what span is. Span is asking, or is the question, whether the vectors can be expressed as a linear combination of the vectors that you're considering. That's what span is. Span is all possible ways of writing the vectors as linear combinations. Okay, so A is good. All right, so I have a lot of requests. So let me just go back. Leo, yes, I will do my best to complete the answer key. The answer key is on Blackboard, but it's not complete. So you can see what I have at the moment. The only thing that I'm missing are like the bases and what else am I missing? The linear independence, bases, and dimension. Yeah. So right now I'm doing one of them that's not there. So if there's a row reduced echelon form with a pivot in every column, those are the coefficients and it's in the span. Yeah, so the idea of the row reduced echelon form, right? This always gets you the information for the solution to the system. So this is the system, right? Or the matrix equation. And so when we row reduce, perform row reduction, and we get the row reduced echelon form, then we can we see that we have 3 pivots, and these 3 pivots are associated with the 3 columns that are associated with the 3 variables or the unknowns. So that's good. So everything worked out here very nicely. There might be a situation where one of these vectors may not be in the span. So maybe the question would be, what would that look like? I would repeat the same steps, right? The same steps, and I would get a matrix, an augmented matrix, and I would make my calculator perform row reduction so that it gets to the row reduced echelon form. And if I get a row reduced echelon form of a matrix where the bottom column, I have where you see the 3 pivots, where I have zeros here, if I had a 5 here or any other number other than 0, it would indicate that this system is not solvable. There's a no solution to it. Why is that? Well, in the bottom equation, what this bottom row is saying is that zero is basically saying zero plus zero plus zero plus zero. I mean, sorry, 0 plus 0 plus 0 equals 0. So you see all of these here, right? They're basically coefficients of equations. That's why we're able to do this. C1, right? We're saying C1 is equal to C2 because this comes from the original equation, what? 2C1 plus 3C2 minus C3 equals 2. This is basically what is written here. Okay, so you always have to be mindful when we have these kind of overdetermined systems where we have more rows than columns in our matrix, in a coefficient matrix. And when we perform row reduced echelon form to get it, you have to be mindful of those rows at the bottom. If you get a whole bunch of rows of zeros like this, everything works out very nicely. The moment you have almost a row of zeros and you get a number here that's non-zero, then that indicates that this system is there's no solution to it. So, okay, does that make sense? Okay, so given the time and given all the other questions, I'm gonna move on to the next. Okay, so Saida was next. This is, can you do 1.21c? So 1.21c. So this one here, 1.21c. Yes. Okay. So this should be quite straightforward, I hope. What is the norm? This is a straight definition. The norm is the components, each entry squared. You add those up and you take the square root. So in this case, u would be what? 2 squared plus negative 2 squared plus 3 squared. So this should be what? This should be 4 plus 4 plus 9. And this should be what? The square root of 17. And then the norm of v is what? The square root of 1 plus negative 3 squared plus 4 squared. Square root of 1 plus 9 plus 16. So then this should give me the square root of 26, right? So this number here should be the square root of 17 plus the square root of 26. You can write this as a decimal, but I would prefer it as a exact value. Is that good? Make sense? Okay, good. All right, next. So wow, I have a lot here. 2.2 part 3, 2.2. What happened with 2.2? All right. Let's see. So I guess a lot of people are having trouble with 2.2. I see a lot of 2.2s. Okay, so let's go to 2.2. So it's kind of like what we've done here, right? With number 3 a little bit. IG spans or just bad luck, huh? So I guess the spanning is what people have trouble with. Okay. Let's see, 2.2 part 3. Well, we did some of that. Let's see who else had 2.2. 2.2 number 3. Okay, so we did some of that. 2.2 number 1. So any one of these, I guess. Like, what must something be in order to be in something? Yes. So Mir, that's exactly what I try to explain. That's exactly what I've been trying to explain with the one we just went over. What does it mean to be in the span? It means you can be written. It means that the vector that you're given can be written as a linear combination of the set that you're dealing with, the set of vectors. So, for example, if we're talking about polynomials, right? So here we have 3 polynomials that are given to us. And the question becomes, the question, this question that I'm doing is um it's just like the one we just did with number 3. It's the same idea. But I just want you to start to see. So the question is this polynomial, let's do part A, okay? Is this polynomial in the span of these 3 polynomials? That's what the question is asking. And I hope you start to see, sorry, hold on. I hope you start to see like kind of the flavor behind this review sheet. Nearly every problem has 3 kinds of vector spaces we're dealing with. We're dealing with the regular Euclidean vector space, which is the R3, R4, R2. Those are like the standard ones that we're accustomed to. And then we're dealing with polynomial space. So we're dealing with vectors that are considered polynomials. And then we're also dealing with matrices themselves as they're being treated as quote unquote vectors in their vector space. So this pops up a lot in the different categories, whether it be spanning, whether it be linear independence, whether it be bases, right? Almost in every subcategory, you've seen polynomial world, you've seen, or I should say polynomial space, matrices, and the space of matrices, and regular Euclidean space, R2, R3, and R4. So the idea is exactly the same, guys. I am asking, so this is number 2, part A, okay? And then hopefully things start to click. So I'm asking, is the polynomial that I'm given P, is this, the question, is this in the span of P1, P2, P3? Is it? Reformulate this question. If you reformulate this question, what would that appear? I'm asking, can I express P of X as a linear combination of the set P1, P2, P3? That's the question I'm asking about span. Span is, equate that immediately with linear combination. That's what it is. So then that is why I write, oh, is it? I don't know. Let me see. C1, P1 plus C2, P2 plus C3, P3. Guys, these are the coefficients of the respective polynomials. So we say this is our first polynomial, second polynomial, third polynomial. So it kind of makes sense to say this is our first coefficient, second coefficient, and third coefficient. These indices are just connecting to the index that we're dealing with, the polynomials. And then what we ask is, what is P? What is P? Let me pull it up here. P is negative 9 minus 7x minus 15x squared. That's P. What's P1? What's P1? P1 is 2 plus x plus 4x squared plus, what's P2? 1 minus x plus 3x squared. What's P3? P3 is a 3 plus 2x plus 5x squared. Do you guys follow? All I did was I replaced the P, the P1, the P2, the P3 with their respective polynomials. And guess what I do after this? I can multiply these, distribute. Everybody good so far? Is this okay? And then what do? I reassociate. I associate with like terms. So these are my like terms, my coefficients, right? My constants. Then all the ones that have the x's in them. Oops, I forgot the x here. So a lot of this is just bookkeeping. And then after that, should be 4C1. So the indices also matter a lot. They matter a whole bunch. Do you guys follow what I'm doing here? And then why did I do this? Because I'm saying one polynomial is equal to another polynomial. So that means that the constant has to match up with the constant. The linear term has to match up with the linear term here. And the squared term has to match up with the squared term here. So then look what I get. My first equation is 2C1 plus C2 plus 3C3 equals -9. My second equation, C1 minus C2 plus 2C3 equals -7. And my last equation is 4C1 plus 3C2 plus 5C3 equals -15. And guess what I got? Guess what I created again? A system of equations. So this idea of span with polynomials is reverted back to a system of equations that I need to solve. So now, not merely am I solving system of equations for the sake of solving system of equations, the solution to the system tells me what, well, if the solution exists, it shows whether or not this can be written as a linear combination. That's right. From here, I can write it as a matrix equation. So I can write this as 2, 1, 3, 1, -1, 2, 4, 3, 5. C1, C2, C3 equals -9, -7, -15. And so now, Gershon, you're in luck because this is a coefficient matrix that's 3 by 3. So if 0, 0, do we just replace -9, -17 with 0? That's right, Ken. That's exactly what we do. And you start to see this is a column vector of a polynomial. What's the polynomial? It's this one. Do you see how the first entry is the constant? The second entry is the coefficient of whatever x is. And the last entry is the coefficient of whatever x squared is. So I could have treated each of these guys just the same. If you notice, these numbers here appear in the columns. So see, these columns are the coefficients of P1, P2, P3. Do you see how nice and beautiful and consistent and elegant this is? Now from here, I can either go two ways. I can either try to consider this as AX equals B, right? Because A is a square matrix. So because it's square, I can see whether this is true, whether this exists. Or I can actually do the full-fledged row reduced echelon form. So let's see. How can I explain this? This is like when you have a quadratic equation. When nothing else works, you apply what? You do the quadratic formula. So the row reduced echelon form is like the quadratic formula to solving systems. Well, you don't always want to be using the quadratic formula because sometimes it's very tedious and annoying, as the same thing as row reduced echelon form can be, right? So sometimes it's very nice, it's very convenient, it's favorable when your system or your coefficient matrix is invertible. Well, it's tantamount, similar to how quadratics can be factorable. So that's the idea. So if it is factorable in terms of quadratic equations, which is the same thing as saying if this is invertible, then immediately we can solve for x1, C1, C2, C3. which is the same thing as saying, hey, is the determinant non-zero? And all these different ways of those equivalent statements for saying whether a matrix is invertible or not. All the things that we talked about in the last lecture, that whole list can be also utilized to determine whether a matrix here is invertible or not. So then from here, I think you can take it on, right? Is this starting to clear up with in terms of span and how span is related to linear combinations and how we get the system of equations, and then this whole ordeal of row reduced echelon form or finding the inverse. So yeah. So if there is a solution, meaning that if this matrix is invertible, then boom, boom, we got the coefficients. What does that mean? P is in the span of P1, P2, P3. If in our attempt to take the inverse of A and then multiply, and then there's some error with your calculator of some sort, then what does that mean? The system, there's no solution. If there is no solution to the system, that means that there are no C1, C2, and C3s that can help express P as a linear combination P1, P2, P3. Is 1A correct? Let's see. It looks like yeah, I think there might be a yeah, it should be. I think yeah, this is a typo for yeah, I think that whole one. Yeah, that whole so I'll fix that. So 1.1, number one, the components, that's like the easiest question here. I think that whole section there has to be corrected. So I'll correct that. Okay. Yeah. That whole section right there has to be corrected. Because when you find, okay, let me just briefly mention this, okay? So when you have like vectors like P1 and P2, so if you have like, call it AB and then call this CD, then when you write P1, P2, this is just going to be P2 minus P1. So it's going to be C minus A, comma, D minus B. So you're just subtracting the x coordinate of P2 with the x coordinate of P1, and then the y coordinate of P2 with the y coordinate of P1. So, okay. Yeah. So that's, I don't know why that, because some of these answers are from a particular textbook. So good thing. Thank you for letting me know. So thank you for letting me know if you see any other corrections or anything that doesn't seem right, please let me know. Okay, so are we good with span? Is span okay? I hope it is. I hope it is. Okay, so let's see what's next. A lot on vector section is different. So is it all of, I think only probably 1.1, right? I think only 1.1 has like 1.1 number one and number two. I think everything else though should be good. To summarize, if it works as a linear combination, basically to span that, no, it's not that it's basically it's exactly what it means. If it is a linear combination, it's in the span. That's exactly what it means. That's right. That's right. Okay, so we've done number 2. 2.2 number 3. A. We've done 2.2 number 2. A. And then let's do number 2 on 3.3. Or number 3. Let me see. Okay, there's a lot here. 2.1 number 3. So subspaces, right? Yeah, I think that's where we're headed to next. So then you had numbers here. So Chaitanya says 2.1 number 3, 2.4. So 2.1 number 3. So this one here. Okay, so how do you determine whether something's a subspace or not, right? So to determine whether a set is a subspace, you only have to worry about 3 things and 3 things only. You have to say, it's check whether is the 0 vector in the sub. So to determine whether a set, I'm gonna call it W, is a subspace of a vector space V. Okay. So the question is 0 in W? The second thing is if U is in W and V is in W, is U plus V also in W? This is called close or closure under addition. So if you have 2 things in a vector space, if I add them, do I get it back? Do I get that sum? Is that also inside the set? If it is, then it's closed under addition. So you need closure under addition. And the last thing is if we have a scalar, if C is a scalar, meaning that C is like some kind of number, and V is in the space or in the set, is C times V also in the set? This is called closure under scalar multiplication. So to determine whether a set is a subspace of a vector space, then all these 3 conditions must hold. If one of them doesn't hold, then it's not a subspace. So to show something's a subspace, if it is a subspace, all these 3 things you must show, and it must be true. If one of those conditions fail to hold, then it's not considered a subspace. So if we look at this problem here, right, we have part A says, is the set of all polynomials who has this form, A naught, A1, A2, and A3 x cubed, for which A sub 0 is 0. So I'm going to write it as this. So W is the space of all polynomials in the space of P3, okay? That's what I'm saying. So this whole thing here, this whole entire thing here is saying that the polynomial P is a cubic polynomial. So P is inside P. A subspace of any vector space, that's right. When we're referring to a subspace, immediately, inherently, we're speaking about a underlying vector space. So that's how we started this whole conversation of vector spaces, right? We just talked about the idea of what a vector space is. And a vector space is a set that contains 2 operations, addition with the vectors and scalar multiplication. And then we had those 10 axioms that have to hold. So every vector space has those 10 axioms that hold. And then what was, I guess, more involved after we discussed this general idea of vector space. No, you don't have to remember all those axioms. Primarily, as you can tell from these questions, what I really care about, or what we tend to care about in linear algebra, is understanding subspaces. So a subspace is it's basically saying it's a vector space within a vector space. But because we're assuming that we're already within a vector space, we don't have to check all 10 axioms, because that would be the more thorough way to go about it, right? You would go through every single axiom and see if all 10 hold. But since we're already within a vector space, the space of polynomials, P3, we're not going to go through every single axiom. So within this polynomial space, this vector space of polynomials, I'm considering a set within it. As you can tell, I didn't say subspace yet. I'm just considering the set. I'm considering the set of all polynomials in P3 where the coefficient or the constant is 0. So I'm saying the constant is 0. Now my question is W a subspace of P3? That's the question. Is W a subspace of P3? That's the question. Is it a subspace? Well, let's check. First thing, is a 0 in W? Of course, now we have to be particular. The 0 vector in W would be what? What would be the 0 vector in W? Wouldn't it be 0 plus 0x plus 0x squared plus 0x cubed? Isn't this the way we would describe 0 vector in the space, right? And as you can tell, is this inside of this? How do you determine whether it is inside the set? Well, you consider this is like the condition to be in the set. We're saying, hey, look at all the polynomials that have a constant equal to 0. If the constant equals 0, then that polynomial is inside here. So this is a much more abstract way of seeing whether something's inside of something, right? So it is, isn't it? The constant here, a sub 0 equals 0. So yes. Next, if I have, in this case, I'm going to call it P1. If P1 and P2 are in W, is P1 plus P2 also in W? That's the question. Do you guys see what's going on here? So P1, what is P1? There's a lot of abstraction here. And there's room for you to name things very in the way you would name it. Like you don't have to call it P1, P2. You can call it something else, but I'm calling it P1, P2. I'm saying I have one polynomial. I'm having another polynomial. What happens if I add these two polynomials? Will I still be in the set W? Well, let's call this P1. Let's be more specific with P1. Let's call this, I don't know. Well, to be in W, P1 has to have 0 in front of it, right? 0 as a constant. Then the next one would be what? I'm going to call it AX plus B x squared plus C x cubed. Okay. Again, I'm not making B, A, B, and C anything specific. I'm just naming them as coefficients. And then call P2 another polynomial in W. So the constant term must also be 0. And this is some other coefficients, dx plus EX. I'm going to use another one. You see, these are when the letters, like, I don't know. E, usually we use it for exponentials. So the next big thing we have is R x squared plus S x cubed. Okay. And they're all constant. These are all constants, coefficients. What happens when I add these together? What do I get? What's P1 plus P2 become? Well, doesn't it become 0 plus A plus dx plus B plus R x cubed plus C plus S x cubed? What did I just show? What did I just show? I showed that P1, P2 is what? Is it inside of W or not inside of W? It's inside. It's an element of. It's a member of. It belongs to, right? Do you guys see that? So it belongs to W. So what did I just show? I showed closure under addition. So any, and the reason why I showed it is because this is any polynomial in W. I chose two random ones, two arbitrary ones, and I show that if I chose two arbitrary ones, I add them, I get a polynomial that's also in W. So then it's closed under addition. And then lastly, what happens if I have a scalar and I have another polynomial in W? Is C times P also in W? And do you see where this is going now? Well, C is anything, right? Some scalar. If I multiply by this, so I'm gonna let P equal what I had here, P 0 plus AX plus BX squared plus CX cubed. So I do C times P, I get C times 0 plus AX plus BX squared plus CX cubed. And you know what? Let me use a different variable coefficient for that. So then this is going to be what? This is going to be 0 plus CAX, C times A times X, plus C times B times X squared, plus C times D times X cubed. What else did I show again? I showed that C times P is in W. Why is it W? Because it's still a polynomial of degree 3, and 0 is a constant again. So then what's my conclusion? W is a subspace of P3. This, again, this line of questioning and showing is for every single time, for every single problem that's in here, or any single time you see a problem like this, you have to show, is 0 in it? Is it closed under addition? And is it closed under scalar multiplication? If all those these three things are true, then what happens? It's a subspace. If one of those three conditions fail, then it's a subspace. And you can now kind of go through them without having to go through every single step, and you can kind of see whether or not it's going to be a subspace. So this is the subspace, as you can tell. Is B going to be a subspace? So this is the set of all polynomials of degree 3, where if you add up all the coefficients, they add up to 0. If you take that set of polynomials, is that considered a subspace? Well, the first thing is the 0 vector in this set, or the 0 polynomial? Usually that's like the easiest one to show. It is, right? Because if you get the polynomial that's all zeros, then of course they all add up to 0, don't they? So that's kind of easy. What if I have two polynomials whose coefficients add up to 0? What happens when I add those polynomials together? Will the result still have coefficients that add up to 0? Yes, right? You can kind of foretell that already. And if I have a polynomial that has all the coefficients that when you add up give you 0, and if I multiply that polynomial by a scalar, will the result also still have a sum of coefficients that add up to 0? And the question, yes. So then all this is a subspace. Do you see that? I can, without having to write one thing down, I already know in advance it's going to be subspace. So what happens when something's not a subspace? I look at part C. C is not a subspace. Well, is 0 in it? Yes, it is actually. 0 is in it, right? Why is 0 in it? Because 0 are all what? Yeah, the test you have to write something, of course. The 0 polynomial are all what? The coefficients are all what? Rational, aren't they? 0 is rational. So 0 is embedded in this set. If you have two polynomials that have rational coefficients, when you add those two polynomials up, aren't the coefficients still going to be rational? Right? So yes. So check one, check two. Now the problem is this closed under scalar multiplication? So that's where something goes wrong. Why does something go wrong? The problem is scalar multiplication has to hold for all scalars, for all real numbers. Scalar is a real number. That's why we say C, right? We say C is an R. R is real. What happens if that scalar is no longer rational but irrational? What if I multiply this polynomial that in the set by radical 2? The coefficients originally were all rational numbers. I multiply by radical 2 to every rational number, A1, A2, A3, A0. Will the result still be rational? Obviously it won't, because I'm multiplying by an irrational number. So this set here is not a subspace. Why? Because it's not closed under scalar multiplication, because I'm multiplying by a scalar that when I do that, the polynomial is no longer in the space, is in the set. It's no longer in the set. It's outside the set. Yeah, closure fails. Closure under scalar multiplication fails. So because of that, it is not a subspace. You guys understand? So then you can do that for this one as well. Think about whether, why can't you assume A0? No, we're not assuming that they're all zeros. We're look, a lot of this stuff at this level is basically just look at what they give you. What do they give me? They give me a set of polynomial of degree 3 for which all the coefficients are rational. And that's all I think about now. I only think about having polynomials of degree 3 that have rational coefficients. That's all I care about. So the zero polynomial is considered to be part of this set because a zero polynomial has zeros being all the coefficients, right? They're all zeros. And that is indeed a rational number. All zeros are rational. But what we're trying to show is that this set here, this entire set of polynomials is a subspace. And what we realize is when we try to show closure under scalar multiplication, it no longer holds. Closure doesn't, because I can multiply this polynomial that have rational coefficients. I can multiply that polynomial by an irrational number. That's perfectly legal because an irrational number is still going to be a real number. It's still a real number. So if I multiply a polynomial that have rational coefficients by an irrational number, then automatically the coefficients are no longer rational. They're irrational. And because of that, that stops the this goes against the third condition where scalar multiplication results in a and the product results in being within the set. But I just showed you that if I were to multiply by an irrational number, that product is no inside inside the set. And so henceforth, scalar multiplication is not closed, and therefore the set is not a subspace of P3. It's not. So that's the idea behind subspaces. And this goes for polynomial space, right? This goes for the same idea here. This goes for R3, Euclidean space. So then the question is this a subspace? Well, is 0 in it? Yes, 0, 0, 0. If you add up 0, it equals 0. So 0 is in it. Is it closed under addition? So if I have two vectors in R3 who adds up to 0, if I add both of them together, will I still get a vector whose sum of the entries also gives me 0? Yes. And then if I have a vector and I multiply it by a scalar, will that vector who's multiplied by a scalar also have entries that when you add them up also be equal to 0? Yes. So W1 is what? Subspace. Do you guys see that? What about 4C? Wait, Xavier, what do you mean by for number 4? The one that I just did. What happened? I just showed that it is a subspace. I didn't write it all down. I want you guys to be able to determine before writing anything down whether something is a subspace or not. And if you aren't able to do that, that's okay. Are C and D not a subspace? Wait, what are you talking about C and D? Are you talking about these C and D, this C and D? For number 4? Yeah, C and D. I haven't talked about C and D yet. But C and D, for example, C and D immediately, C and D are not subspaces. Very easily done. How is it so easy? Because the first thing we check is if zero's in it. Is zero in it? Well, if zero was in it, then this would have to add up to 5, but it doesn't, right? The zero vector doesn't add up to 5, the entries. So W3 is not a subspace immediately because 0 is not in W3. So we can't even talk about subspace. So W4, look at W4. This is the space of all vectors in R3 where the entries are all bigger than 0. Well, immediately the 0 vector is also not in this. Why? Because all the entries are zeros. But we're saying that it has to be bigger than 0. So then 0 is not in W4. So what does that mean? W4 is not a subspace. Does that make sense? And the same thing happens for the matrices, the world of matrices. Is the set of all diagonal matrices a subspace? Well, is the 0 matrix a diagonal matrix? Technically, it is, right? Because to be a diagonal matrix, the only requirement is that everything that's non-diagonal are zeros. Well, the 0 inherently matrix has all the entries in that are not in the diagonal, in the diagonal that goes from the left corner to the lower right corner. They don't have to be zeros, but everything else has to be zero. So then it is diagonal. If you add up two diagonal matrices and you add them together, it's still going to be diagonal. If you have a diagonal matrix and you multiply that by a scalar, you still have a diagonal. So you see how the idea is that you're in the set because zero is in it. Summing two things in the set will still be in, you still be in the set. And when you multiply by scalar multiplication of a scalar, that matrix is still going to be in the set. It's still diagonal no matter how you dice it. So that whole set of diagonal matrices in themselves is a subspace. So you see how this is like a common theme, right? Matrices, polynomials, matrices, polynomials, and R3 and our Euclidean space. Having fun, guys, or what? You guys feeling good? Okay, so let me just go back to see what we've done and where should we go next. So 2.44, 2.45, 3.3, 3.4. So a lot of people have been doing 2.3. Yeah, so 2.4, right? 3.3. So it looks like there's several people going 2.4, 3.3. 2.4. Okay. Hold on. 2.45 is fine. Okay. Yeah, so we can do this, yeah, instead of 4, right? So this whole section on bases, as if you notice, it says show that something's a basis, right? So then again, P3, M22, R3 is like the common thing. So don't be afraid when you see that on the test. This is gonna happen. You're gonna have some kind of concoction of P3, M22, and R3. So number 4 and number 5, these are just little problems that are connected to the plus minus theorem, which states that if you have, for example, in this case, right, if you have a set of vectors, and if one of the vectors is in the span of the other 3, for example, then you can eliminate that vector from the set. Because if a vector is in the span of the other 3, then immediately it creates a linearly dependent set. So to create a basis, remember you need 2 things. You need to be able to span and be linearly independent. So it's kind of implied that this set of 4 vectors are going to be linearly dependent. So one of these vectors is a linear combination of the other 3. So whenever you have a set of vectors where one of the vectors is a linear combination of the other 3, if I were to eliminate that vector, I don't change the span. The span stays the same because this other vector is a bit redundant. It's redundant in the act of spanning. It's redundant. So that's why we take it out. And so when we take that out, the idea is that if you continue doing so, you get to a point where you can't reduce it any further and you create a basis. Okay. Now you can also go the opposite way. The opposite way is when you have a set of 2 vectors that are linearly independent. And what we can do is we can add more vectors to the set until we have a spanning set. So a basis is exactly that balance of being spanning, it spans, and being linearly independent. That's a basis. It's both. If you have a set that's smaller than the number of basis elements, then you have a linearly independent set, but it doesn't span. If you have a set of vectors that are more than the number of vectors in the basis, then you don't have a linearly independent set, but you do have a spanning set. So because we already kind of know, right, R3 has a dimension of 3, then we know that if we have 2 linearly independent vectors, all I need is one more vector to be included and make sure that that set is linearly independent, and immediately it becomes the basis and immediately it spans R3. So this is very specific. It's saying find the standard basis vector. What are the standard basis vectors? E1, E2, E3. One of them. Choose one of them and include that as part of the set of these 2 vectors. If they're linearly independent, then what? Then it's going to be a basis. If they're not, then disregard the one that you chose and choose the next one. That's the idea. Does that make sense? So how can we determine which vector is going to produce a basis? How can we determine that? So remember, so the idea is that we have linear independence. And how do we know they're linearly independent? Neither is a scalar multiple of another. So there's nothing I can multiply V1 by a scalar to get V2 and vice versa. There's no scalar that multiplies it. And you can tell right away, because if there were, I can make -1 become a 1 by multiplying by -1, right? But this -1, when I multiply by 2, gives me -2, which is almost there. But when I multiply -1 to 3, I don't get -2. So that's why V1 is not a scalar multiple of V2. And therefore, V2 is not in the span of V1. And therefore, because you're not in the span, you're linearly independent. Oh, what do you mean by RE identity? Yeah, so I think what you're saying is that what I'm going to do is I'm going to create a set. I'm going to say, hey, you know what? Let me check this out. Is this a linearly independent set? How do you determine that? Remember how we determine linear independence? We set up the same idea here. A linear combination, guys. This idea of linear combination is essential to this whole test exam. The question now is, you see how this is a specific vector is 0. The vector is 0. Normally we have, like when we talk about span of whether something's in the span of the other set of vectors, this is a non-zero vector. But in this case, for linear independence, this must be 0. So we're checking. How do we check this? This becomes C1, what? -1, 2, 3, plus C2, 1, -2, -2, plus C3, 1, 0, 0. And what do we get again? System of equations, -1, 2, 3, 1, -2, -2, 1, 0, 0. C1, C2, C3, 0, 0, 0. So there's so many ways to think about this. And Satar, you're right. What you could have done is just create a system, a matrix where the columns are the vectors themselves, which is exactly what we just did. And if this column, if this set of vectors, right, if I find a row reduced echelon form of this, and if that equals the identity, then what does that mean? That means that they're all linearly independent. If I don't get the identity, so if this equals the identity, so if the row reduced echelon form of A equals identity, then vectors are linearly independent. Right? If the row reduced echelon form does not equal the identity, then vectors are linearly dependent. And you can check that in various ways. You can also check whether the determinant equals 0 or non-zero. If the determinant equals 0, then it's linearly dependent. If the determinant is non-zero, then the set is linearly independent. So you see how all these different equivalent statements come back again and again and again. So if you try this, so -1, 1, 1, 2, -2, 0, 3, -2, 0. So if I do row reduced echelon form on this matrix, I get the identity. I get the identity. The moment I get the identity, what did I just show? The vectors are what? Linearly independent. I have 3 vectors that are linearly independent in a space whose dimension is 3. So what does this immediately become? This is a basis. Done. That's how I did it. Yes. It's linear. You get, because you have 3 linearly independent set vectors in a space whose dimension is 3, you automatically get span. Like it just comes automatic. You don't even have to check for span in this case because I already know the dimension of R3. But that's the idea. That's the idea behind this problem. Okay. And B works the same idea. It's the same way. Okay, so let's move on to 3.3 because I think I got several people saying 3.3. Yeah, so change of basis, right? That's when things, so determinant is non-zero. Yeah, so Baldwin, don't forget the equivalent statements. Think about it. If the determinant is non-zero, how is that related to the row reduced echelon form being the identity? If the determinant is non-zero, that implies invertibility. Invertible matrices have row reduced echelon form being the identity. So they're equivalent. It's an equivalent statement. To me, for me to say that the row reduced echelon form of a matrix is the identity is equivalent to me saying that the determinant of that matrix is zero. It's the same. No, the determinant of that matrix is non-zero. It's the same thing. Because the determinant is non-zero means that the row reduced echelon form is the identity, which means that the vectors are linearly independent, which means that the solution to the system is unique and exists, which means blah, 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 all those different statements, they're all the same thing. So if I say one thing, I say them all. That's the whole point. That's what I'm saying. You can check this idea of linear independence in so many different ways. One way, row reduced echelon form. Another way, determinant of that matrix. Another way, whether the solution exists, and so on and so forth. But the best ways are either row reduced echelon form, which always works, or if you have a square matrix, use the determinant. If you don't have a square matrix, you use the row reduced echelon form. Do you expect examples for questions asking us if a space is a subspace? I don't exactly understand what you mean by expect examples for questions. So if I ask you whether something's a subspace, it's going to look like very much the same thing as what we've just done. I don't know what you mean by expect examples. You don't prove a set is a subspace by using examples. You prove it by arbitrarily choosing something in that space and showing whether that arbitrary selection produces is closed under addition and scalar multiplication, and that the zero vector is inside. In order to know the dimension, you must, well, that's a good question. The dimension is defined to be the number of elements in the basis. So it kind of seems to proceed, right? You have to know how many basis elements exist. And then you just establish what the dimension is. Once you establish the dimension, then things kind of come. So we kind of already know that if you're in Rn has a dimension of n. Why is that? Because you have standard basis elements, E1, E2, all the way to En. Yes. So that's the key, Sam. So that's why I've tried to explain it in this capacity, right? The way I'm explaining subspaces, I'm utilizing arbitrary representation. I think that's something that maybe is new for some of you. And it's very commonplace in mathematics to say, it's like saying, let something be this. So I'm saying, let P1, P2 be in W. If that's the case, then P1 looks like this. P2 looks like this because I have coefficients and I have the zero constant term. Oh, Saida, there is no calculator row reduced echelon form at all when you prove subspaces. Subspaces has nothing to do with calculators at all. I did not use any calculator to show subspace. A subspace is dependent upon three things and three things only. These three things. And when I say show that something's a subspace, I expect for you to show me like this. The importance is the line of reasoning. That's the importance. So this is showing subspace. Spanning is completely different. Spanning is more computationally intensive. So you start to see now the complexity of linear algebra. There's a very technical, computationally heavy, intensive aspect of it, while at the same time being very theoretical and arbitrary. You understand? So the subspace aspect of vector spaces is very abstract, pure, theoretical. The idea of spanning is more computational. Okay, so the spanning is definitely, you have row reduced echelon form, you have a lot of real numbers you're dealing with, concrete examples you're dealing with. Whereas with subspaces, it's purely based upon the way the set is defined and how we are applying these conditions of subspaces to that set to determine whether that set is indeed also a subspace. Okay, so let's do like I said, I can go on and on for this. 3 point, yeah. So for 3.3, that's probably the change of basis and all that, right? Like that's where things get pretty interesting, right? So I gave you a lot of change of basis examples. All right, guys. So I'm gonna go up until 9:30. Okay. And then we can we'll see if you guys get a little earlier tomorrow, because I'll be here since I'll be available after 9:15, which is the first exam that I'm giving. So between 9:15 and 10 o'clock, we can have last minute discussions about any of this stuff in the class. Okay. Yeah. Ahmad, you can look at that information is on the CUNY Blackboard. The room and the building is Rathis. I don't remember if it's in the second floor. I don't remember exactly which one, but you can check on the announcements in Blackboard about all of that. Okay, so the change of basis. Eventually they all start to look alike, right? Thank you, Leo. Okay. So just to get our feet wet with this, one is very nice. It's very straightforward. You have two bases. You have one called B and the other one called C. So again, this is a basis for R2. We're in R2. So we expect two vectors to be a basis. And we want to find a matrix P that goes from B to C. Do you guys see that? It doesn't say that explicitly, but if you see P is being, you multiply P with the coordinates relative to B, and then you get the coordinate of X relative to C. So to understand change of basis, you have to understand the preceding category, which is coordinates relative to a basis. So you see how very sequential this is? So to understand basis, to understand change of basis, you need to know coordinates are relative to a basis. To understand coordinates relative to a basis, you have to understand linear combinations. Linear combinations of bases, which are linearly independent and span. So all of this stuff is like interlaced. It's connected. Okay, so you have to go from the ground up to really understand things in a very intuitive way. So just to get number one, it's a very procedural step. To get the transition matrix, call it T, and I'm going from, where am I going from? I'm going from B to C, or written B to C like this, right? What we do is we take the new basis and create a column vectors of those, and then an old basis. And we perform row reduction. We get the row reduced echelon form of it. And the idea is that you get the identity on the left side and you get the transition matrix on the right. So in this case, the old here is B and the new here is C. So this is old, this is the new, this is C, and this is B. So the idea of transition matrices, finding them, is actually not the hard part. I think the conceptual part of it is harder, but the actual procedure is not as hard because you have a calculator that does this all for you. So the new bases are what? 2, 1, and we put them as column vectors, and 3, 2. And what does matter though is the order. So again, bases, again, this idea of ordered bases is important. The first one that you see is the first basis vector, and then the second one is the second basis vector. So then I care about the order. First one, this is the second one. And then the same thing happens with B. I care about which one is first, 2, 1, and 3, 2. Wait, I just wrote that again. Sorry. 5, I should be 5, -2, 1, 5. So 5, -2, 1, 5. So when I put this in my calculator and I find a row reduced echelon form of it, I should get the identity. And then I should get on the other side the transition matrix. So let's do that real quick. I'll get the matrix. I'll get the 2 by 4. 2 by 4. So this is 2, 3, 5, 1, 1, 2, -2, 5. Then I will do the matrix. And I do row reduced echelon form on that matrix A. So this row reduced echelon form business appears again and again. And look what I got. I got 16, a -9, -13, 9. So the transition matrix from B to C is given by 16, -9, -13, 9. Again, finding the matrix itself shouldn't be the hard part because the computations are done by your calculator. If you do them by hand, then yes, it gets annoying and it gets kind of there's a lot of room for error because of so much computation. You're solving systems of equations individually, but this procedure simplifies things very nicely. So that should be number 1. Okay. Is that clear with this? Good. And so then when you do things that are not just vectors, so it gets a little more maybe confusing when you have matrices like number 4, or when you have polynomials like number 5. Do you see what I've been saying? R3, M22, P3, or P2, I should say. Well, Mir, embedded in all of this is the relative coordinates. So I hope I can probably, as they say, kill 2 birds with 1 stone. Like, for example, number 4, okay? So let's look at number 4. It's probably the last one, guys, okay? I know you guys can go on and on with this, but I don't wanna be the reason you guys don't wake up on time. So look at number 4. We have two two bases, and yeah, this is the more complicated one. We did a problem like this in lecture. We did a problem like this actually I think last class. So the idea is that we're in a lower triangular set of matrices. Lower triangular are matrices who have zeros above the diagonal. So you see all of these, right? The only entry above the diagonal is that upper entry, the upper right entry. They're all zeros. So I want to find the transition matrix from C to B, right? So C is the old here, and B is my new. So remember we did this with upper triangular matrices. So this here, -1, 0, 0, -1. And then we have 0, 0, 3, 4. You got -1, 4, 4, 0, right? The idea is to have the old basis vectors and the new basis vectors. I mean, the new basis vectors here and the old basis vectors here. The question is, how do we represent this as a vector? That's the difficult part, because so the idea behind this particular kind of problem is, what's the dimension of this subspace? This is a subspace. Yeah, so again, to do this problem, I would revert back to the previous lecture that we had the on Wednesday, because we did a problem just like this with upper triangular. It's literally the same problem. The reason why I did lower triangular is just to give you a different look, because really it's the same thing if I said upper triangular. It's the same problem. It's just now it's lower triangular. If you're a lower triangular 2x2 matrix, then you have the dimension of that space is 3. Do you guys see why? Remember, dimension also is another way to say degrees of freedom. So if you have a 2x2 matrix, you have 4 entries, but one of the entries will always be 0, no matter what. The other 3 entries could be anything. There is no restriction. So because you have 3 entries, and you have 3 possibilities of choosing those entries, then you have a dimension being 3. So the dimension 3 here indicates that this space is similar to R3, because R3 also has the same dimension. So that's when it gets more abstract, right? This idea of having R3 space being similar to a space of 2x2 matrices where they're all lower triangular. So in a way, we can treat this guy as a vector, -1, 0, -1. And then this guy here as another vector, 0, 3, 4. And then this guy as another vector, -1, 4, 4. Right? Yes. For the second column, you should say, Sam, not in second matrix. Second column. And then the next column would be what? All the ones with C, the C basis, right? So this would be what? 1, 4, 3, 2, -2, -2, 1, 1, 0. Does that make sense? Now, to really see all of this very clearly, go back to that lecture that I'm speaking of, the most recent one. And you saw the reason, you would see the reason why this is okay to do, because you could have also said, why don't we do -1, -1, 0? Why does this have to be -1, 0, -1? But when you see how we did the whole system, it works out to be that this is the correct way of representing such a matrix as a vector. So then once we have this, put this in your calculator, find the reduced echelon form of this. You're going to get 1, 0, 0. You're going to get 0, 1, 0. You're going to get 0, 0, 1. Now the question is, what's on the right? So I'm going to do that. And this is going to be a 3x6 matrix. So it's going to be -1, 0, -1, 1, 2, 1, 0, 3, 4, 4, negative. Oh. Sorry about that, guys. Went too fast. So 0, 3, 4, 4, -2, 1, -1, 4, 4, 3, -2, 0. Okay, so we're going to do row reduced echelon form of this 3x6 matrix. Whoops. And I get -7, -8, 7, -6, -6, 4, -8, -9, 7. For upper triangular, you would just do the 2 and the bottom right. Yeah, the top 2 and the bottom. Yep, that's exactly right. Oh, it's not letting me share. Okay. So this is my matrix that goes from the C to the B basis. Once I have this matrix, that's part A. So TCB, that equals -7, -8, 7, 6, -6, 4, -8, -9, 7. What about B? It says find the coordinates M in the ordered basis B. I want to find this, Mir. This is your coordinates relative. I want to find M relative to B, but I'm given the vector of M relative to C. You see that? So I am given whatever M is. I don't know what M is yet, but I know that M is written in terms of C. What do I have though? I have the matrix that takes things from written in C and I express it in terms of B. That's what this matrix does. So what I'm going to do is I'm going to multiply the T matrix by the coordinate of M relative to C. When I multiply this column vector by this transition matrix, the result is the coordinates relative to B. That's the beauty behind this. So now I can write this like in this fashion: -7, -8, 7, -6, -6, 4, -8, -9, 7. Multiply this by M. What is M? They gave that to me. 3, -1, 1. Multiply this. So let me go back. So I'm gonna do a 3x3 matrix. So the 3x3 matrix will be -7, -6, -8, -8, -6, -9, 7, 4, 7, right? That's my transition matrix. Then I'm going to go and create the 3 by 1 matrix that's already there for me. And my 3 by 1 matrix is 3, negative 1, 1. Then I'm going to go out and I'm going to multiply A, my transition matrix, by the column vector that I just inputted. And look what I get. I get negative 23, negative 27, 24. Let's see. Let me see, 1. So you apply the transition matrix not to the original vector. You're multiplying it to the coordinate relative, the vector coordinate, the coordinate vector relative to the basis. You see? So when you do that, you get the transition matrix. But let me just give me 1 sec. Oh, yeah. Okay, and so then the idea, you guys see? So the idea now is what? This matrix, this column vector is the coordinate vector of M relative to B. So do you see what happened? This is the coordinate vector of M relative to C. I multiply the transition matrix from C to B, and now the result is the coordinate vector of M relative to B. And then the last thing here is to do what? Find what M is. I don't know what M is. I know what M relative to B is. What is M relative to B? Negative 23, negative 27, 24. But what does this mean? What does it mean to have a coordinate vector relative to B? Remember, these are the coefficients of your basis elements. That's what the coordinate vector relative to a basis is. It's saying, hey, I have this thing. I'm expressing this vector in terms of a linear combination of the basis vectors. This is a basis. And I'm expressing a vector in terms of that basis. In doing so, I create a linear combination. With that linear combination, I have a unique way. That's the whole point. It's the uniqueness of it. There's a unique way to express a vector in terms of the basis elements, the basis vectors. There's a unique way to express it. Because it's unique, it's like saying it's like a code. Instead of me writing M, the matrix, the 2 by 2 matrix, I'm going to write it as a column vector, negative 23, negative 27, 24. But that code is embedded with B. B is like this is like the blueprint. This tells me everything about the space. So instead of calling M a 2 by 2 matrix, I'm gonna call M a column vector. That these numbers here are a code for which elements of the basis I'm using, how much I'm using. And B has what? B has, these are my elements. This is my M1, my M2, and my M3. So I can write this like this. Negative 23, what is M1? Is negative 1, 0, 0, negative 1. Negative 27, M2 is what? 0, 0, 3, 4. And then 24 is, M3 is what? Negative 1, 0, 4, 4. And then when you add this all up, what do you get? You get negative 23 is positive. You get negative 1. You get 0 up here, of course, because upper triangular. And then you get, what do you get? You get negative 27 times 3 plus 24 times 4. Sorry, negative 27 times 3 plus 24 times 4. I get 15. And then lastly, I get 23 minus 27 times 4 plus 24 times 4. And I get 11. So my original matrix M was this. Do you follow? Do you guys see the connection between coordinates relative to a basis? What I did was I figured out what the original matrix was. Why? How? Because this original matrix was rewritten as a linear combination of the basis elements in B. As such, I could have done that as well. I could have figured out what these numbers were as well. This is the idea of span. How do I write the basis elements as a linear combination of M? They did it for me. I didn't have to do that part. Yes, Mir.
So just to confirm, the way to find the coordinate vector of any matrix or vector within a space is to write it as a linear combination of the basis, right?
Yeah, one more time.
The way to find the coordinate vector, let's say of two vectors, in relation to a basis, is to write the basis as a linear combination of those two vectors, right? And then solve for the constants. I think I got it. I'm just confirming.
I think you're saying, I think you're understanding, but the way you said it was incorrect. The way to find the coordinate vector of a vector relative to a basis, right? A vector. It could be any length, but it's a vector. Or it could be a matrix. It could be a polynomial. The way to express that as a linear combination, the way to find the coordinate vector relative to a basis is to express that vector as a linear combination of the basis vectors.
Got it. So I had it mistaken and I would have gotten it wrong. So thank you.
Those coefficients that represent the scalars associated to that linear combination, those coefficients become the coordinate vector.
Got it. Right, because they're relative to
They're relative
the basis,
to the basis.
just like in our good old standard one, they're relative.
Exactly. The standard one is the easy one because it just feels right. It flows. It makes sense. So if you have like 1, 2, 3 relative to the standard basis, right? It's going to be 1, 2, 3. Why? Because you have 1 of E1, 2 of E2, and 3 of E3. So obviously, this is the way we represent any vector because it's the standard way. But what if I want to represent 1, 2, 3 with other vectors? I don't know, like 1, 1, 1, 1, 1, 0, and 1, 0, 0. This is a standard. This is a linearly independent set of vectors, as you can tell. And it's in the three-dimensional space, so it spans the space of R3 because the dimension is 3. So then if you were to figure out what C1, C2, 3 is here, that would be the new way to represent 1, 2, 3 in terms of these basis vectors. So if I call this B, right? 1, 1, 1, 1, 1, 0, and 1, 0, 0. So the important thing is identifying what the basis is. That's important. That's very important. And if you just now start to see the importance of bases, your whole life, when we talk about the XY plane, R2, right? The basis, standard basis has always been these two. The E1 and E2. That's why the way we write things out, right, is so nice and standard and organized. They're all what? It's like a grid. It's a square. Of course, I can't do this. What I want to try to demonstrate to you is something that I can't do with my given technological limitations. But this is where many of you guys probably have heard of this guy, 3 blue, 1 brown, or is it 3 1 3 1 brown? I don't know. One of those combinations of 3 1 and blue brown, right? In his way of explaining it, right? He does a very nice job of showing what really is happening as a transformation. You actually start to see why it's called transformation. The way we view the world is a very standard way so far in R2. But the moment you have another set of vectors that are linearly independent and span the space, then you redefine the space based upon those vectors. So for example, if I choose the vector, I don't know, 1, 2, and 1, 0. No, let me use another one. 1, negative 1. Actually, negative 1, 1. So then what happens with this? The idea is that now every other vector, if I redefine my space using these two basis elements, every vector is now redefined based upon these vectors. And so your XY plane is now morphed. This instead of E1 being the standard now, quote unquote, now it's 1, 2. Where's 1, 2? 1, 2 is like somewhere here. So now everything along this line is kind of like my x-axis. And then negative 1, 1. Everything along this line is now behaving kind of like my new y-axis. I guess we can call it like x hat, and then y hat. And then every point is now going to be expressed as a linear combination of these two vectors. And so your space is now going to be reimagined. Something like this. Of course, like I said, I can't replicate what will transform into this kind of new grid-like structure. But that's the idea. I hope you get the gist of what I'm trying to say. Yeah, he's done stuff for Khan Academy. Yes, he's worked with Khan Academy. But do you understand what this relative coordinates business is dealing with? That's what this is saying. I'm redefining my space in terms of other basis elements other than E1, E2, E3, or the standard basis. We've learned mathematics with that basis in mind the whole time. Now, through linear algebra, we're saying let's redefine our space with other vectors, because sometimes expressing it in other ways, it's more advantageous than just using the standard 1, 0, 0, 1. And so now this, you start seeing like this element here that had a particular expression with the standard basis now has a different expression with respect to these two bases. And then you have a new way of expressing the space. That's the power behind it. Okay. U plus V, the norm of this is literally adding U plus V and then taking the norm of that vector. So for example, if U was 1, 2, 3, and V was 4, 5, 6, how do you add U plus V? You just add 5, 7, 9, right? But then I'm going to take the norm of that vector, which is taking the square root of each entry squared. This is like the generalization of the Pythagorean theorem, which is used. The Pythagorean theorem is really used to define distance between two points in space. And now this is a three-dimensional space, so we're finding the distance between the point 579 and the coordinate 0, 0, 0. So in doing so, we apply the Pythagorean theorem. Now we extend that to the three-dimensional space, which takes care of this. We take care of that by squaring every number, adding that, and taking the square root. And that will give you the length of that vector. Wow, guys.